TFTs from string theory.
Hi. First, let me thank the organizers for this nice workshop and giving me the opportunity. I would like to tell you about the BF theory, which tells us about the possible choices of global structures for given quantum filtering. It's defining one dimension higher. And I would like to tell you how to get this from string theory. Okay. So it was originally thought that to specify quantum filter, it's enough to know it's a spectrum of local operators and their correlation functions. But we now know that the extended operators are also important and they can have symmetries, and this has consequences for our filter. So, in fact, there are theories which have the same local structure but different global structures, and this is the result of the real charge quantization condition, a generalization of it, and this is nicely explained in this paper where I'm solving a problem where they, for example, look at 4D super-Yang theory with Liège over SU2, and this theory can realize different global structures. So we could have extended operators in this theory, which are tooth lines and Wilson lines, and also dynamic lines, and depending which ones you have in your theory, you get different global structures and different gauge groups. So my purpose of the talk is to tell you about how to get these different symmetries and how we can obtain them using a string theory, but there are a lot of motivations why these symmetries are interesting, and for example, there are work done by people in the audience, I'm missing some, sorry, but we can learn about constants and RG flows, we can learn about dualities, and there are a lot of other interesting things in the Yang theory standard model that are consequences of these symmetries. But I will not discuss any of this today. There are people who would know a lot about this, so you could ask more about in the audience. But what I want to do is to study these, use string theory as a tool to learn about these field theories, their symmetries. So I will start by telling you how you can realize these symmetries from field theory, from a string theory perspective, and then I will go on to tell you how to see these possible choices by studying the BF theory. Okay, so we know that, so also one motivation for studying it from a string theory is that in this analysis where they study the higher forms from, in this paper they use the gauge theory description to study these. They use the gauge rule, but sometimes you have non-Lagrangian theories that are hiding something. You don't have this description, and string theory gives us this method to find these symmetries. So, for example, what we do, we put like, say, an element-dimensional string theory, which is M theory, on some product manifold, and the geometry of the internal manifold, which is C2 mod, then tells us about what kind of symmetries we can realize in our 7-dimensional field theory. So in M theory you have branes and these have different cycles. So if my internal manifold here is C2 mod Zn, if I modify it a bit, it looks like what I have down there. And there are cycles in the bulk of this geometry, and there are cycles which are defined relative to the boundary. So if you identify all the points on the boundary there, you get these green cycles. And when branes have these cycles, you get different objects in your theory. There are, if you wrap the cycles in the bulk, you get dynamical objects, and then if you wrap the cycles which extend to infinity, you get defects, like the Wilson lines and tooth lines. And these defects can be screened by the dynamical objects. And we want to look at the subset of these defects which are not screened. So we take this quotient by the cycles that extend to infinity, to the asymptotic boundary. And that gives us the defect group, but this is not exactly the group of higher form symmetries. Also, please stop me to ask questions, because I know maybe this is not everyone's familiar with this. So
can I ask a question? So what is this geometric engineering? You take M theory and you construct a field theory without the Lagrangian? Is that the point?
Yeah,
Is that what you mean?
You don't have to have a Lagrangian. So,
Right. So some of them are with Lagrangians, presumably, and some of them are abstract.
yes. I mean, it depends what theory you're engineering.
And they are conformal. What I mean, or
Yes,
there's all kinds.
Yeah, there are all types of different theories you can engineer. They're supersymmetric usually, but they don't have to be conformal. It's depending on the geometry that you choose.
And is there a particular class that you're interested in? Or
So this should apply to any theory that you like, that you should be able to do this for any theory that in principle you get from a string theory.
right, but you in particular, your
So
talk
I'm
is
just
about.
looking at this dimensional theory, mostly looking at this example where you have n equal 1 supersymmetry and it's a super conformalistic theory.
And so, sorry, maybe I didn't understand. Is that one theory or is that a class of theories?
So this theory that I will get to, like, this theory can have different possible global symmetries. So it's a relative theory, but once you fix the symmetry, then it becomes an absolute theory.
Okay. Thank you.
Any other questions?
So what do you mean by defect group? What does it mean?
So it's the group of the, so you know the defects that you have in your theory, these are the extended objects, which they form a group, which is called defect.
Do they have to be topological or any defects?
So these are the topological defects.
They are topological.
Yeah.
I see.
So you mentioned that it's not the higher form symmetry.
Yes.
What's the difference actually?
So this is a bigger group. It's because here we include all the possible line defects or higher dimension, or it depends what dimension we're in, but here we have all the possible defects, and this is related to the fact that we, like in this 4D example, we couldn't have all the possible lines, and then we have to choose a subset to fix this. Any other questions? Okay, so exactly how can we see from a string theory that this is not the higher form symmetry group? This comes about when you look at how the symmetries are realized from a string theory. So in M theory you have fields, the field content includes G4 and G7, which are fieldless actually. But so these, when you reduce on this four-diagonal that we had, you get background fields for higher form symmetry. So in the 7-dimensional theory, you have background for one form symmetry, which is B2, and you also get the background for the 4-form symmetry, which is C5. You get these from reducing G4 and G7. And it is known that these fluxes in a string theory, they don't commute. There are those papers out there, they discuss it, and this in turn means that these, when you reduce on the manifold, this non-commutativity of the M-theory fluxes means that your symmetry generators, which are given by exponential of the integral of these background fields, they don't commute with each other, and so they cannot be mutually local in your theory.
So that's the anomaly, right, between the backgrounds.
So we don't usually call this an anomaly because the field theory doesn't know about all these possibilities. It only knows about one symmetry, but I guess from a higher dimensional perspective, sometimes people call this an anomaly between these symmetries in a way, but it's more about a choice of global structure that.
And what is L?
So here,
linking.
Yeah,
linking.
exactly. It's the linking. So in the 11-dimensional manifold, if you look at the boundary, there are cycles which they are linking each other, and this is exactly why they cannot be separated. And these fluxes, they don't commute.
Sorry, but
Yeah.
I guess in the question that Tim was asking, there are ways to think about it. So you could think of anomalies of the theory, of the field theory, or you can think of anomalies in M theory, and it's like that's an anomaly in M theory.
Yeah, so from a higher dimensional perspective, you can think of them as anomalies.
But in M theory, it's just a commutational relation of some operators. Right? That's not necessarily an anomaly. I mean, I was thinking that it's an anomaly in the.
Yeah, but it's just saying.
Okay.
So I think what I'm going to discuss the BF action, it actually looks a bit like an anomaly polynomial in a sense. So that's, I guess, and it's defining one dimension higher than, and maybe I refer to that and see.
Can I just understand the setup, because maybe I didn't understand.
Mm-hmm.
So where does the field theory live?
So on M7.
So
So 7 dimensional.
So that's where field theory is.
Yes.
And what these extra pieces are somehow.
So this is the internal manifold here, C2 mod Z, and this is.
And is that somehow gapped? And I mean, you can throw it. I mean, it's kind of.
We integrate
Can I think
over
of?
it.
Can I think of it as an SPT phase in some sense, or is it not a good anomaly?
I don't think so. I'm not sure. But I mean, usually when you do compactification, you say these are small dimensions you can see, but we have non-compact manifolds. Yeah.
Nothing is on the boundary of anything else, is that right?
Not yet.
Yeah, okay.
Oh, okay.
You shouldn't think of it. Okay, yeah.
So nothing is on the boundary. Thank you. So these are all without boundaries.
Yes.
Wonderful.
What is the field theory on SUM?
It's a super conformal field theory n equal to 1 field theory.
Wait.
It's 7.
Well, it's SUM.
SUM super maximum space. Sorry. Yeah.
8 supercharges.
Yeah, super charge.
Rounding theory is 8 supercharges.
Not conform.
It's not conformal.
Sorry. Sorry, yeah, 16.
16 supercharges. Yeah, okay.
And at the moment, M7 is any 7-dimensional manifold, is it?
Yes, I mean it's closed. It doesn't have a boundary,
Okay.
and it's
And
spin
it's
because we want to spin it, but nothing.
And it has time being non-compact, or should
Time is non-compact?
Yes.
In M7? Okay.
So it's time times some threefold, for example.
So I have a fixed M7, so I guess time is just one direction. Okay, so we see that these symmetry generators, they don't come in with this interns, but I already kind of said that the best we can do is pick a maximal commuting set of these operators, our symmetry generators that we had here. And then, depending on what maximal subgroup of these we pick, we get different higher form symmetry groups. So going back to the case of 4D angle stories, we find that when we calculate these defect group, we find that it is a 2 plus a 2, and picking a maximal commuting set of these operators corresponds to picking maximal subgroups of the defect group. And then we can reproduce the 3 possible choices where we have electric conform symmetry, magnetic, or the diagonal one. Okay, so what we can see that there's a theory, BF theory, defined in 1 dimension higher than R. So here I'm talking about the 4-dimensional image theory. There is a theory which describes these possible choices of global structures known as the BF theory. And here B2 and A2 are the backgrounds for the electric and magnetic one-form symmetries that we had there. And the 4-dimensional theory lives on the boundary of M5. So when we choose boundary conditions for these fields, we can reproduce these choices of global structure. And this generalizes to manifolds in higher dimensions, where the BF theory, we could have like a Q form symmetry and a D minus Q minus 2 form symmetry, describing the BF theory by this action for a quantum field theory which is D-dimensional. And here the status space of this theory reproduces the choices of the higher form symmetries that we can have in our field theory. There are some recent papers discussing the BF theory from a field theory perspective. Any questions? Okay, so what I want to say is how can we obtain this PF theory from a string theory perspective? Because we saw from this flux non-commutativity that we cannot realize all these symmetries, but we didn't really find this PF action, which is a good way to describe these choices. And so this PF, actually, before I get to how to find this BF theory, I wanted to say there is this notion of symmetry theory, and the BF theory is part of this symmetry theory. So if we are talking about 7-dimensional field theory, then the BF theory would be defined with integrating over this 8-dimensional manifold is defined in 8 dimensions, and then there is also the symmetry theory also contains anomaly theory for this field theory in 7 dimensions. So there are all these anomaly polynomials which also are defined in 1 dimension higher, and possibly in principle it should include other structures that we can realize, like non-invertible symmetries and so on. You should be able to discard them in this 1 dimensional higher theory.
So is that extra dimension now extra on top of your M theory, or is it part of your M theory?
So the way it works is, so here we have M11 is C2 mod Z times M7. What we do is we rewrite this in a way, should I include that? But we can, so C2 mod Zn is, we had this, so here C2 mod Zn can be defined as a cone over S3 mod Zn. And if you take M11 to be S3 mod Zn, then you get an interval times this 7-dimensional manifold. I mean, if you deform the singularity to get something like this, and then this is an interval. And
so the extra dimension is embedded there?
Yes, it's
okay.
in there. So we put M theory basically on S3 mod Zn, and then we get 8-dimensional theory, which would be the symmetry theory for our field theory on S7. So how do we get this BF theory from string theory? Well, we saw that we had a hint that these current symmetries come from these fluxes in M theory, and we know the V2 background field comes from the G4 flux, and the background for the 4-form symmetry comes from G7. So a good guess would be maybe we can look at the kinetic action in M theory, which has the form G4 with a star G4, and get this BF theory from that, knowing that G4 and G7 are dual in 11 dimensions. But if you try this naively, it wouldn't work, and we need to do things differently. So what we really need to do is to construct a self-dual action for this G4 and G7. And to see how to do that, we can look at the example of parallel scalar in 2 dimensions, which is self-dual. And there, naively one would write an action d5 with the star d5, but we know this is not a very good action. It doesn't include the self-duality constraint. So what we can do is try to define a Chern-Simon for it in 1 dimension higher. And this is, we can do it by coupling to a background field A, and the action would be to be that. And then under gauge transformation, we see that the change in this action is lambda dA. And this is exactly the change in the action of the Chern-Simon theory in 1 dimension higher. A with dA under the gauge transformation delta equal to d lambda. So we can take this Chern-Simon to be the action for the self-dual field. But this is not a very good action because it may be globally not well defined if these fields A are not globally, if they are topologically non-trivial and they are not globally well defined. People usually go to 1 dimension higher and write F fetch F for F being the field that stands for A. But we don't need to do that. We don't have to have it to be able to define an extension. So what we can do is instead we can use the language of differential cohomology. So you know,
Sorry,
in
do you mind going back to the previous slide?
Yeah.
I didn't get how the inclusion of the background field helps with the self-duality. How
So-
do you see the scalar self-dual?
so when so what we do is here entry is boundary of the boundary of entry is M2, and then we impose boundary conditions on A to get so. What we can do is to think about this differently. I start with this action and add to this boundary term with A wedge star A, and then we can integrate A out and put boundary conditions there, and then that boundary condition also then we'll find some solution A equal to G phi. And then by imposing the boundary condition, we'll see that it's self-dual. Don't sorry, that's not.
It's not a background field.
Sorry?
It's a dynamic or background field?
So it is a dynamical field in M1 and 3, but yeah, we use when the scalars there appears when we impose boundary conditions.
Oh, I see. So you consider it as a dynamical field in the bulk and then impose some boundary
Yes.
conditions which, because of the anomaly, you have to have a scalar, chiral scalar, basically, on the boundaries.
Yes, exactly. So I was saying that I want this action to be globally well defined. So what we can do is use this language of differential cohomology. So we usually take our fields to be just differential forms. But if you have more interesting topologies, then that is not sufficient, because then you can have, for example, if you consider Klein bottle here, if you start on the surface to go back to the same point, you have to go around it twice. This means there is a one cycle which is torsional, and if you have interesting topologies like this, you have to consider more generally your fields to be valued in differential cohomology, where you have the curvature part, the drawn part kind of, and then there is another part, H2 of X with coefficients in Z, singular cohomology, and there you take into account these non-trivial topologies. And so we're just gonna promote our fields to live in H2 instead, to take this into account, and there is some relation. So what we do, we can rewrite our action in terms of these new fields, which we promoted our A's to be, and we can define a well-defined action in 2 dimensions.
Sorry, so is the problem here that usually, as you said, you go to 1 dimension higher to define the Chern-Simons theory, in 1 dimension lower, nothing depends on the extension, but now you have Chern-Simons with the boundary.
Yes.
Is that the problem? You can't go to one, is the boundary the problem, or why can't you just lift up?
You can, but it's nicer to just don't.
Intrinsically, you want to define it
Yes,
intrinsically.
this is like
or
a better language to describe it, I guess. I guess there could be, depending on what manifolds you're on, there may be abstraction to lifting into 1 dimension higher and writing a 4-dimensional manifold in higher dimensions, but I think that's a better way.
So what is a U?
So
What is
it's-
this beast?
So this has the 2 parts. There is the curvature part, there is the topologically non-trivial part, and these are related by some relation, and there is another trait.
Okay.
Yes, it's too quick.
I believe you, it's better. The problem is I understand this one, I don't understand this one.
Can you say physically what each of those 3 parts captures? I think that might help people like me who skate by.
So this part is kind of tells you about the curvature.
Okay.
That part tells you about, well, if you have torsion, it tells you about that, but more generally it tells you about whether you have some H2 extra structure.
Is that the flux? I think that's the flux.
Uh,
I think the H2 part.
H of A.
H2, yeah. H2 part, I guess.
The
Is that
H2 part.
Yes.
I think that's the flux.
I'm not sure what you mean by flux.
Like for ordinary E1H2.
flux of the A integrated over?
I think that's correct because if you triangulate manifolds, then IA is corresponding to integer one.
Mhm.
Yeah.
Attached to the bracket.
So it's an
right?
integer,
yes.
the quantized one. And if there are any comments also.
Yeah, we can maybe.
Okay, so what I wanted to do is to apply this kind of construction to define a kinetic action for M theory. So there we have G4 and G7 fluxes, and G4 is not self-dual, but if we take these two as a pair, then you get a self-dual fit, and you can do exactly the same thing as in Chern-Simon theory, in the same thing as the Carl scalar, and construct an action for this G4 for this pair in one dimension higher, so M12. And then once you go and reduce on a stream of Zn, so we are in 12th dimension, and then the boundary of this is the 11-dimensional theory that we were talking about before. And once you reduce on this space, what you get is some fields which live on a stream of Zn, T2, that these are torsional fields, and then you get some fields C5 and B2, which were the backgrounds we had before, that live on W9. And then integrating these out, you get some coefficient, and then you see that the BF term emerges here. So basically we put M theory on this 12-dimensional manifold, and then we integrate out the parts that live on a stream of Zn, and then we are left with some action, which is the BF action.
Here, so is it important that length space has torsion?
Yes, yes, exactly. So if we consider some geometry where we didn't have these horizontal cycles, then this would vanish. Yeah.
What is X8 here? It's a 7-dimensional manifold plus the radial coordinate.
So X8 is this where it's the boundary of X8 is where the 7-dimensional manifold lives. So
No, sorry, I don't understand. Is on the boundary of the boundary trivial?
we have manifolds with corners here, kind of. Yeah. So that's it. Basically, we see that there is this BF term, and we can modularize all these higher functions at the same time. So I was saying this looks a little bit like an anomaly term. So maybe in that sense.
It should be, right, from
Yeah.
the point of view of 7-dimensional theory.
From the 7-dimensional point, it's not, because it doesn't know about these possibilities.
Oh, sorry, I don't understand.
So the 7-dimensional theory has either, say, this symmetry or this symmetry, but not both. And it doesn't know about all these different distinct possibilities. Like in 4D angles, you had the different one-form symmetries, and your field theory doesn't really know you can have electric one and magnetic one.
But why don't you have both of these on the... Just because of presence of background, you mean, or...
So it's because, I mean, we saw that this flux non-commutativity, and you know that they cannot, these backgrounds cannot be locally mutual.
Yeah, that's right. But if you take away the backgrounds, then there's nothing. Everything commutes, and that's.
Basically, she is saying that we have to choose whether a gauge group is SUN or SUN mod G.
Okay.
So my kind of, so I guess we can. Okay, so discuss how we can see these different global symmetries, starting from string theory, and that to see this we need this language of differential cohomology, which is important because torsion, as pointed out, is what gives us these non-trivial BFRs. And there has been much work on this. Sorry, I'm missing some names, but there is a lot more to be done here because we want to see the full picture where all the other more general symmetries, more categorical symmetries are also included. And also, we could apply this formalism to find symmetries of many different filters that might be interesting to different people, and then apply, and then try to look for applications and see what interesting physics they imply. Okay, thank you for this.
Is there any more questions?
So if you include categorical type symmetry, what kind of extension is possible? Could you give one example?
Well, I mean, we haven't found any. There were some recent papers yesterday.
Okay.
Yeah.
You asked many questions.
And so is it also, so can we also apply it to 4D case as written in?
Yeah, so in 4D, we can start from type 2B and then try to
I see.
do the same thing
so
there.
That is included.
Yeah, so
I see.
that one is also possible.
With anomalies, you can do descent, you can go 2 dimensions higher, right? So can you do the same for this symmetry?
Yeah, I mean, yes, you can go 1 dimension higher here as well.
But these are very different from anomalies, right? That's something entirely different. They're not convertible to TFTs. That's quite
There's no more question. Let's thank Sophie.